in this lecture, we'll see boundary effects in convolutional functions built in Matlab and Python. You should first understand that there are three different modes for the computation of convolution in Matlab and Python. These are three options: full, valid, and same. If we choose the full option, then at points where the given two arrays overlap partially, the arrays are padded with zeros to get the convolution values there. So the output will be enlarged by about the size of kernel in both directions. If we choose valid, then the output is calculated only at positions where the arrays overlap completely. This mode does not use zero padding at all, so the output is shrinked by about the kernel size in both directions. Now, for the same option, the function crops the middle part out of the full mode so that its size, output size, is the same as the input size. In Matlab, the first array is the input, and in Python, SciPy, the larger one is input. So we have boundary effects in convolutions, and post-processing is required if you want to suppress boundary effects or get the convolution result having the same size as the input. See this example. We choose a function f of xy sine pi x times cosine pi y. We want to find the Sobel derivative in x directional derivative by convolving this filter, and we'll try to observe boundary effects and try to suppress the effects. Here we'll see codes implemented in Matlab and Python. In Matlab, we'll use the function conv2, and in Python, we'll try to use a function from SciPy signal, the convolve2d, and we'll try to choose three different modes. And to suppress the boundary effect, we'll try to expand from the valid smaller one and around the boundary to make the output the same as the input. The convolution results are plotted to compare. Basically, we want to compare with visual inspection. Okay. This is Matlab program using conv2, conv2. Now we choose 21 points in one direction and generate mesh grid. And over the mesh grid, we evaluate the value, function value, sine pi x and cosine pi y. Now we save the true derivative to the array fx, and that is true derivative. Now we define the kernel and scaled to compare with the true derivative. Now, by using full option, we save the output into fx full and same, then here the same, and valid and valid. Now this one is enlarged, and that is the same size as input F, but that one is smaller, and from each side one grid line is short, so that is smaller, and there is one grid line more in every side. Okay. Now for expansion, here after opening an array, we assign at interior points the valid convolution result, and now the around edges we simply copy the values from inside the points. For example, this is array, then inside here is copied from valid, and that the boundary lines we copied from just inside, so that is the constantly expanded. So we did that way. Now for Python, we can do it in the same way. So here we choose now 20 points, and same way we made a mesh grid, and NumPy is quite Matlab-like, so that you can implement many programs. It looks like Matlab. Okay, here we have f and fx, the true derivative, and the same way here by using the convolution function with a full same valid, we made it the same way, and then for expansion we did exactly the same way as in Matlab. Okay, now we see the pictures from Matlab. This is true x directional derivative. This is x-axis, that is y-axis. Now, once you are using the convolution with a full option, then it is enlarged. That one is 21, but it is now 23 and enlarged. And along the boundary, we have here some other values, and these are useless values. And if you try to use this output without care, then you may make a big mistake. And if we choose the same, then yet again, because even though it's the same size in convolution, we have to use a line of zero padding, so that we have here around the boundary we have some wrong values, useless values. Now if you see the valid, then even though is here short, smaller, now this profile is quite reasonable, and then out of that we expand just one line in every side, then we get this one. So this one, the finally expanded output, is quite similar to the true x derivative. Now how about Python here? Now this is x direction and that is y direction. So the coordinate system, coordinates are rotated. So we see a bit different way, but basically this one is the same as in Matlab. This is true x derivative, and by using Python, we have a full, along with a full option, we have some problems around the boundary. And again, even though you do with option same, you have some undesirable values around the boundary. Now, if we choose valid, then here, even though the size is smaller, every value in this output is okay and has some accuracy. Now, from this one, now we expand and around the boundary, and then we get the same size output. That one seems quite good approximation, and that will be much more useful than the earlier this output. So once you try to use convolution, then always you have boundary effect, and either the size is small, or and if size is the same or large, then you have some unreliable values around there. So you have to deal with that. And the reason the convolution functions have such output is here. In fact, once you know what the kernel is, and once you understand the purpose of this convolution, then we can deal with boundary points more effectively. However, in general purpose programs, the functions doesn't know about your intention, so that just simply zero padding is used. And there are so many cases based on the kernel, so that it's not easy to deal with automatically. Just simply zero padding, and the other area inside, the value is far from zero, then around the boundary, your output will be really very odd. So it looks like very wrong, but it's not really wrong. If you know how to use it, then these functions are quite useful. So that's the reason I try to say something around there. Okay, that's it. Thank you.